Welcome to The Explainer. Today, we're diving into network security. And I want you to think about this not just as a technical issue, but as a high-stakes digital detective story. It's this constant, relentless arms race between the people protecting our data and those trying to break in and steal it. Just to give you a sense of scale, look at this number. 3 billion. That's how many malware attacks were reported way back in 2010. Can you even imagine what that number looks like today? We're literally swimming in an ocean of digital traffic, and somewhere in that ocean, threats are lurking. And really, that brings us to the core question, the big problem we're tackling today. In a network that has trillions of perfectly normal, legitimate data packets zipping around every single second, how on earth do you spot the one that's malicious? How do you find that single tiny needle in a digital haystack that just keeps getting bigger and bigger? So, to find something, you've got to know what you're looking for, right? Let's get on the same page. What exactly is a network anomaly? This definition from 1980 is just perfect. It holds up so well. An anomaly isn't just something that's a little bit different. It's something that is so out of place. It practically screams that it was made by something else. It shatters the pattern. It's the one piece of data that makes an analyst lean in and say, whoa, hold on. That's not right. And these anomalies, they tend to show up in 3 main flavors. First, you have a point anomaly. That's a single, sudden event, like a huge data download from a server that's normally pretty quiet. Then there's a contextual anomaly. This one's all about timing. Think about an employee logging into the company network at 3 a.m. from a country they've never been to. The login itself is normal, but the context, that's super suspicious. And finally, you've got collective anomalies. These are a bunch of events that look totally fine on their own, but when you see them happen together in a sequence, they spell trouble. Okay, so we know what we're looking for. Now let's talk about how we've tried to find it over the years. The history here is a really fascinating arms race, so let's start with the first generation of our digital guardians. The early systems, they had a massive fundamental problem. See, they were trained on these old datasets from the late 90s, but tech moves incredibly fast. That data became obsolete almost immediately because it just didn't reflect what modern attacks or even modern computer networks look like. I mean, it's pretty simple when you think about it. You just can't catch a cybercriminal from today using a playbook from 1999. So these early methods mostly fell into 2 buckets. On one hand, you had statistical methods. These would build a mathematical model of what normal looked like and then flag anything that strayed too far from that baseline. On the other hand, you had classification. This worked kind of like a basic virus scanner, searching for the specific digital fingerprints or signatures of attacks we already knew about. The fatal flaw? The first method couldn't keep up when normal was always changing, and the second was completely, utterly blind to any brand new attack it had never seen before. And this is where the arms race really took a huge leap forward. Defenders realized they needed a totally new kind of weapon, something that could actually learn and adapt on its own. It was time to teach the machines how to see the bad guys for themselves. Machine learning brought 2 powerful new strategies to the table. Supervised learning is like studying for a test with an answer key. You show the machine tons of examples of what's good and what's bad, and it learns to tell them apart. But unsupervised learning, now this was the real game changer. It doesn't need an answer key. You just feed it a colossal amount of normal data. It gets so good at understanding the patterns of normal that it can instantly spot anything that doesn't belong. Even a totally new, zero-day attack that no one has ever seen. This is how we started finding the unknown unknown, which, of course, brings us to the present day. The tools we have now are incredibly sophisticated. We're using deep learning to hunt for threats in ways that honestly felt like pure science fiction just 10 years ago. So today's deep learning detectors have 3 main tricks up their sleeve. The first is forecasting. The AI is constantly trying to predict what the network traffic will look like in the very next moment. If what actually happens is way off from its prediction, boom, that's a red flag. The second is reconstruction. Here, an AI compresses data down to its essence and then tries to rebuild it. The thing is, anomalies don't compress well, so they cause errors when the data is rebuilt. And finally, you've got contrastive methods. This is all about teaching the AI what normal looks like from every conceivable angle, so it becomes a master at spotting an imposter. Now, I know these strategies can sound a bit abstract, so let's make it concrete with a real, cutting-edge example. There's a new algorithm called ANDPED, and it shows just how powerful these new techniques really are. The real genius behind ANDPED is how it handles noise. See, any server has these natural, predictable daily cycles, right? People log on in the morning, activity peaks midday, then it drops off at night. That's all normal, but it creates a ton of background noise that can easily hide a real threat. What Antiped does is it uses a really clever technique to identify and just remove those predictable daily rhythms before it even starts looking for anomalies. And once you filter out all that regular noise, the true threats, the things that actually break the pattern, suddenly pop out and are impossible to miss. So, does it actually work? Oh yeah, absolutely. This chart shows us the detection delay. That's how quickly an algorithm spots an anomaly after it happens. NDP Pro, the enhanced version, has the lowest delay by a pretty clear margin. It's finding threats about 16% faster than other top-tier methods. And in cybersecurity, where every single second counts, that kind of speed isn't just an improvement. It's a critical, game-winning advantage. But, as you've probably guessed, the arms race never ever stops. As our defenses get smarter, the attackers get smarter too. And that brings us to the final part of our story: the challenges that are just over the horizon. Researchers right now are wrestling with some seriously tough problems. How do you possibly run these incredibly complex AI models in true real time across networks that span the entire globe? How are we going to handle the absolute flood of data coming from billions of new Internet of Things devices? Then there's the big one: the curse of high dimensionality. It's a fancy term, but it just means that as we track more and more variables, the data gets exponentially more complex, almost impossible to make sense of. These are the battlegrounds where the next fight for our digital security will be won or lost. And that leaves us with a final pretty heavy question. We've come so far, from just matching simple signatures to building AI that can literally learn the rhythm of daily life to find a hidden threat. But the bad guys are always evolving too. And as every part of our world goes online, our cars, our homes, our critical infrastructure, the number of ways to attack just explodes. So the question isn't just about whether our digital guardians are smart. It's whether they can evolve fast enough to protect a world that's getting more connected and, honestly, more vulnerable with every passing day.